Welcome to our lecture. In this lecture, we will continue with our discussion on TRIAC. In the last lecture, we had an introduction on TRIAC construction, and also a little introduction on the power electronics. In this lecture, we will study about TRIAC operation, TRIAC characteristics, application of TRIAC, and two numerical problems. Now let us see the operation of TRIAC. So this is a simple circuit where this AC supply is connected across the main terminals MT2 and MT1 of the TRIAC through a load resistor RL. So load, power supply and TRIAC. Now this gate circuit consists of a battery, a switch and a current limiting resistor. So this makes the circuit for the gate. Now how does this circuit function? Let us take the case when this switch S is open. When this switch S is open, no current will flow through the gate of this. So the TRIAC will not conduct, it will be cut off. And the only way to make this TRIAC conducting when the gate voltage is 0, gate current is 0, is to give it a breakover voltage. But that is not the normal way in which we use a TRIAC. We always use a voltage here which is less than the breakover voltage, and we turn it on by giving it a suitable gate current. So what happens when we close the switch S, the functioning of the triode? So when the switch S is closed, gate current starts flowing into the gate circuit. So as in the case of SCR, the TRIAC will start conducting with the proper gate current. So the higher the gate current, the lower value of the voltage at which the TRIAC will start conducting, irrespective of the polarities, whether MT2 is positive with respect to MT1 or it is negative with respect to MT1. In either case, it will start conducting with the application of the gate current. What difference does the polarity make? So if this terminal MT2 is positive with respect to MT1, then when the TRIAC turns on, the conventional current will flow from MT2 to MT1. And in the second case, when MT2 is negative with respect to MT1, then when the TRIAC is turned on, the conventional current will flow from MT1 to MT2. So the polarities of the terminals will determine the direction of the flow of the current. Now, from the above discussions, we can note two things. The TRIAC can act as an AC contactor to switch on or off AC load. So that means it can be used as a switch, just as an SCR is used as a switch. TRIAC can be used as a switch. The second advantage is that by adjusting the gate current, we can allow any portion of the positive and half cycles of the AC supply to flow through the load. So this characteristics allows us to adjust the power which we give to the load, the AC power. So based on these 2 points, let us look at 2 applications, each one using one of them. We will look at the application once we study the TRIAC characteristics. So this figure shows the characteristics of TRIAC. In the first and the third quadrant, you will notice that this characteristics is similar to that of the characteristics of SCR in the first quadrant. This is natural since a TRIAC is 2 SCRs connected in parallel. The only difference between these two is the direction of the applied voltage and current flow. So let us note a few points from this TRIAC characteristics. The first point we just mentioned, that the characteristics in quadrant 1 and 3 are identical to that of SCR in the first quadrant. Now, TRIAC can be operated with either positive or negative gate voltage. But in normal operation, the gate voltage is positive in the first quadrant and is negative in the third quadrant. Because with this arrangement, less charge is required to turn on the TRIAC. So depending on the quadrant in which we are functioning the TRIAC, we give it a positive or a negative voltage. We give the gate a positive or a negative voltage so that less charge is required to turn on the TRIAC. As in the case of an SCR, the supply voltage at which the TRIAC is turned on depends on the gate current. So if you have the more gate current, greater the gate current, smaller will be the supply voltage at which the TRIAC will turn on. And this characteristics will permit us to use TRIAC to control AC power in a smooth manner from 0 to full power in a fine manner, and then there will be no loss of power as it is lost if we use electrical methods, if we use resistors in series. Now let us look at the applications of TRIAC. So as we see that low gate currents and voltages at the gate are used to control large load currents and voltages. So TRIAC is often used as an electronic on-off switch, which is controlled by a low current mechanical switch. The low current mechanical switch is switch here, with which we give current to the gate. So this is one application of TRIAC, a high power lamp switch. This is a lamp which is using 1000 watts. Now if you have a mechanical switch just connected in series with this, each time you put on and off, you are joining or breaking the circuit which passes 1000 watts, which will lead to sparks which are dangerous. So we use a TRIAC here, and let us see how using few milliamperes it is able to turn on and off 1000 watt bulb. So this is the circuit. You have the main supply 230 watt 50 Hz going to the lamp which is connected in series with the TRIAC, and the gate is connected with this arrangement, the resistor here, here and direct here. So when the switch is in position 1, that is it is connected here, it does not get any current. So this lamp is off. When the switch is in position 2, then this circuit is formed, due to which a few milliampere currents would flow through the TRIAC, which will turn on the TRIAC and the lamp will be on. So just by connecting this switch in position 1 or 2, we can put on or off this lamp which is of 1000 watts, and here we are using just a few milliampere currents. Another application is electronic changeover of transformer taps. So this is a transformer, this is the primary of the transformer, secondary of the transformer. The primary of the transformer is connected with the power supply. Now you know that depending on the ratio of the primary and the secondary, the voltage step down or step up occurs. So if you want to change the voltage at the output level, you will have to change the ratio of primary and secondary. So in this arrangement, you can change the ratio by activating and deactivating one of the TRIACs. So in the case when TRIAC TR1 is on and TR2 is off, the input line is connected across the full transformer primary, that is from point A to point C, when TR1 is on and TR2 is off. So the primary is from A to C. Now suppose if you want to change the tapping so that the primary is from only A to B, not A to C, then we put off TRIAC TR1 and put on TRIAC TR2. In that case, the primary is only from point A to point B. So in this way we control the number of turns in the primary, either from A to C or A to B. The circuit for the gate current is made in such a way that both the triacs are not put on at the same time. If they are put on at the same time, then B and C will get shorted, which is a dangerous situation. Now let us look at two numericals. The first one, let us see. The triac shown in figure 21.14, that is, this is 21.14, can be triggered by a gate triggering voltage of plus or minus 2 volts. How will you trigger the triac? By only a positive gate voltage, and second, only a negative gate voltage. So you are supposed to make some arrangement here so that in one case it can be triggered only by the positive gate voltage, and in the second case it can be triggered only by the negative gate voltage. So let us take the first case where we want to trigger it only by the positive gate voltage. So for that we connect a diode in series to the gate. So this diode will be forward biased when the applied voltage is positive, and this will be reverse biased when the applied voltage is negative. So only when this applied voltage is positive will the current pass through the diode and enter the gate. So what should be the voltage that we need to apply here? This voltage will be the sum of the voltage drop across the diode, which is 0.7 volt, and the 2 volts required to turn on the gate. So total 2.7 volts need to be applied here to turn on this triac. In the second case, where we need to allow only a negative gate voltage, we just reverse the direction of this diode D1. One more numerical. This is the circuit where 50 ohm is our load, which is connected in series with the triac. The power supply is of 50 volts. This is the circuit which gives the appropriate gate current to the triac. Now we have to find that when this triac is fired, that is when it is turned on, what is the current that flows through this 50 ohm resistor. In two cases, in the first case when triac is ideal, and in the second case when the triac has a voltage drop of 1 volts. So in the first case, when we consider this triac to be an ideal triac, there will be no voltage drop. So the whole 50 volts will be dropped across this 50 ohm. So to calculate current, we use the simple Ohm's law. Current is equal to voltage upon resistance, that is 50 volt upon 50 ampere, you get 50 ohms, you get 1 ampere. 50 volts upon 50 ohms, you get 1 ampere in the ideal case. Now in the second case, when there is a drop of 1 volt across the triac, then the drop across the resistor will be 50 minus 1, that will be 49 volts. Then we use the same formula. Current across this 50 ohm resistor is equal to the voltage drop across it divided by its resistance value, that is 49 volts divided by 50 ohm. So we get 0.98 amperes. Thank you.